Section 8.1 deals with the area of triangles and special quadrilaterals. You want to set this into your table of contents, and then we'll begin. We'll discuss the area of a rectangle, parallelogram, triangle, trapezoid, and kites, or other quadrilaterals with perpendicular diagonals. So to begin first, the area of a rectangle. You're probably familiar. Of course, the area of a rectangle is base times height. The area of a parallelogram is similar. In fact, the area of a parallelogram is the same formula. It's base times height. You'll notice that the height is not a side length in a parallelogram. So why does this work? If you think about slicing off that triangle from the end of the parallelogram and sliding it over, you see that the parallelogram makes a rectangle. And the dimensions of the rectangle in terms of its area would be base times height. We can use a similar strategy for some other area formulas. Let's take a look at the area of a triangle. The area of a triangle is 1/2 base times height. So where does this come from? How much of the rectangle is taken up by that triangle? Why is it 1/2 base times height? One way is to imagine dropping the altitude. Now we're creating two rectangles, one on the left and one on the right, and the triangle takes up half. Now this idea of building a rectangle around a triangle doesn't work if something instead were like this obtuse triangle. So here's another idea. Let's take your triangle and double it. We know that that full shape would be a parallelogram, and parallelograms are base times height, and we only want half. So 1/2 base times height. Next, the area for a trapezoid, the area is 1/2 times the sum of the bases, b1 plus b2, times the height. So let's talk again. Where does this one come from? If you take a trapezoid and double it, you create a parallelogram. Well, and we only want half of the parallelogram. The dimensions there would be the sum of the bases, b1 plus b2, times the height, and then cut it in half. Next, the area of a kite, or anything with perpendicular diagonals, is 1/2 times the product of the diagonals, d1 times d2. So anything else with perpendicular diagonals, this will be good for rhombuses, rhombi, and squares. So why does this formula work? If you imagine splitting your rhombus or your kite right down the middle. Now this is a triangle, right? We've got a 1/2 base times height. The other is also 1/2 base times height. Now the dimensions of these two triangles are let's call the base length d, or d1. The heights would be half of the diagonals. So we're adding two triangles together. 1/2 base times height plus another base times height. Let's sub in the values of the bases and heights. And when you multiply through, you get 1/4 d1 d2 plus another 1/4 d1 d2, and that adds up to 1/2 d1 d2. Section 8.2 deals with applications of area. We'll just talk through one example, and then we'll clean up the pieces in class together. So let's take a look at this example. You'll probably want to push pause and copy down the information you see here. Harold works at a state park. He needs to seal the redwood deck at the information center to protect the wood. He measures the deck and finds that it is a kite with diagonals 40 feet and 70 feet. Each gallon of sealant covers 400 square feet, and the sealant needs to be applied every 6 months. How many gallons should he buy to protect the deck for the next 3 years? With these area word problems, you want to be very organized. List out what do we know and what do we want. Well, in this case, we want how many gallons there are for the next 3 years, how many gallons to buy. And what do we know? Well, we know that the deck is a kite and its diagonals are 40 feet by 70 feet. We also know that 1 gallon of sealant covers 400 square feet, and we need to reapply every 6 months. So it'll be your job to figure out how do you get to what you want given what you know. And we'll talk about the answer in class.